Hello again, everybody. This is Mr. Hoy, and in this video, I'm going to go over how to graph absolute value functions. Here, I've got a Desmos tab open, so you can kind of see how I'm working through this question. I would encourage everyone who's graphing absolute value functions to start with a parent function like I have here, y equals the absolute value of x. What that allows you to do is to see the changes to the parent function that we're going to make by manipulating this a value, or the value here in front of the absolute value, as well as numbers inside the absolute value and numbers on the outside as well. So starting off right away, here's the parent function. When you have x of 1, you have a y of 1. See here, x of 2, y of 2. One thing to note here is if you have an x value that's a negative, like a negative 2, you get a positive 2 for the y value as a result, because when you put negative numbers into absolute values, your result is a positive number. So you get this V-shaped graph here. I'm going to start off with the first transformation, and that's a reflection over the x-axis. So if you have a negative number being multiplied by an absolute value, you're going to take the existing graph and you're just going to flip that graph over. So whatever it happens to be, you put a negative sign there, you flip that graph upside down. Now, let's say you're starting with your parent function and you have a value here in front of 1, and you increase that. So you make that 1 a 2, a 3, a 4, etc. What's going to happen there is the graph you create is going to go up more quickly, or in the case of a negative number, go down more quickly. There's a few different names for this, and this is where it gets a little confusing. You could refer to this red graph as being narrower than the blue graph. You could also say that that red graph is stretched vertically, or it's a stretched version of the blue graph vertically, up and down, taking this graph and stretching it upward. You could also say it's a version of the blue graph that's been compressed horizontally. So imagine you bring your hands together side to side and squeezing this graph in or compressing it in to make that red graph. So again, to recap, the different names for this are narrower, or stretched vertically, or compressed horizontally. Now, if you take the 1 and you decrease it, so you go closer to 0, and you select, let's say, 1/4. What that does is it takes this graph and makes it wider. You call this graph wider than the existing graph. You could also say that it's stretched horizontally. So imagine your hands going side to side, stretching the graph horizontally. Or you could say it's compressed vertically. So you take the graph and you kind of come down vertically. Pushing that graph further down would make the graph, again, wider. That's another way to say that. So again, to recap this one, if you have an a value or value here 1/4, that would be making the graph wider, or stretching it horizontally, or compressing it vertically. Now, let's say you start with that existing parent function, and all you do is you add or subtract a number at the end. What's going to happen here, if you just do this outside the absolute value bars, what you're going to do is move the graph up or down. In my example here, I have -4 or -4, so I moved this existing graph down 4 units. If I were to change that to a +4, now I'm going up 4 units. The most important thing I want you to take from this is the impact it has on this point here. This is called the vertex of the graph. So the parent function has a vertex of 0, 0. The new graph is going to have a vertex of 0, 4. That's because we're taking the y value and shifting it up 4 units. Go back to that existing function. Now, let's say we put a -3 inside the absolute value bars. This is the trickiest transformation in my experience in terms of students understanding why the graph moves the way it does. So our existing parent function was here, our new one is here. We're subtracting 3 inside the absolute value bars. Many students believe that since we're subtracting 3 inside the absolute value bars, we should shift the graph down this way to -3. However, one thing to note here, the vertex of an absolute value function is where the information inside the absolute value, the expression inside the absolute value, equals 0. So the existing absolute value, the parent function, has 0, 0, because when x is 0, the inside of the absolute value is 0 for that parent function. However, if you make it x minus 3, and you set x minus 3 equal to 0, x would be 3, positive 3. That's why this vertex is located at 3 and not at -3. If you put -3 inside of this absolute value, you'd have -3 minus 3, or -6, which is not the reflection point of this graph. So to recap here, if you subtract the number, you're moving 3 units to the right. on the vertex or for the vertex. If I were to add 3 units, I would move 3 units to the left. So just to recap, I would note this particular transformation potentially over the others because it may not be as intuitive for you when you first learn it. Now, this last one I have here includes 4 of the 5 different transformations I have listed here. I didn't include the 1/4 because I have to include either the 2 or the 1/4. Now, here is that graph. Let's start by just looking at the graph. First thing you're probably going to notice is the graph is reflected downward, or it opens downward. Reflected over the x-axis is another way of saying that. This graph is reflected downward because of the negative sign right here. That's the impact that has. Now, you may also notice this graph is a little narrower than the previous or parent function. That's done by the 2. So what the 2 does is it made it narrower, or it stretched it vertically, or it compressed it horizontally. Those are 3 different ways of saying that. The -3, again, we just discussed that a moment ago. What that does is it took the vertex at 0, 0 and moved it 3 to the right. So it moved it here, essentially. The last thing, that +4 at the end, took the vertex that was shifted to here and moved it up 4 units, ultimately to right here. So the vertex we arrived at is 3, 4, because the 3 that's in that vertex would create the 0 inside the absolute value. 3 minus 3 is 0. The 4 makes up the y component, is only created by adding or subtracting a number at the end of the absolute value function. So it's pretty easy to come up with these vertices once you realize the impact that these 2 numbers have on that vertex. The a value, this -2 here in front, has no impact on the location of the vertex. It is only this number and this number that impacts the vertex. If you're looking to graph this, I would strongly encourage you to start with the vertex. So start by graphing 3, 4, or whatever it happens to be for the example you're doing, and then focus on this -2. If you're manually graphing this, you want to find that 3, 4. Graph that first, and what you can do with this -2 is go to your vertex and treat it like a slope at first. If you were graphing a linear function that had a slope of -2, you would go to traditionally your y-intercept, you would go down 2 and over 1 to the right. With an absolute value function, it's basically the same thing. You're going to go to your vertex in this case, you're going to go down 2, 1 to the right, down 2, 1 to the right, down 2, 1 to the right, and continue on there. The difference when it comes to absolute values is that it's a reflection left and right. So as you go down 2, 1 to the right, you finish out that right side. When you go backward, instead of going up in this direction, you'll go down 2, 1 to the left, and you'll finish it out in that direction. Generally speaking, it's easier for students to find the vertex, graph the right side because they're used to graphing slope, and then go backwards with that number here. All right. Thanks for listening. If you have any questions, please reach out as soon as you can.